Welcome back, everybody. So, as I said last lecture, today we want to talk about hardware security as kind of like the last module of this class. Uh, any questions before we get started about project, homework, quiz? All right. So, as I said last time, your project due will be on last day of the quarter, which is the Friday in the final exam week. Your quiz 3, the final quiz would be next week on Thursday. I'm going to release it during the class time. You can either be in person and take it here, or you can just, as usual, just log into your Gradescope and take it there. I'll also post something on campus fire about this, right?
How long do we have for it? Like, what's the window?
It would be during the class time, basically.
So exactly 2 hours.
Yeah, and less than that, because I want to make sure that, maybe like 15 minutes after 10 and then 15 minutes before 12. So like 1.5 hours. Oh. All right, so today I want to talk about hardware security, okay? And the first question is, okay, what is hardware security? What's categorized as hardware security and what's not hardware security? And I mean, the obvious and very clear answer is attacks and defenses that involves the actual hardware is considered hardware security, okay? So, anything that comes because of the physical device and not the software installed in it. So regardless of what software you're installing on this device, you still have that vulnerability. That's a hardware, security related issue, okay? So for example, physical side channels was one of the areas that we discussed already. That's kind of like a hardware security issue, okay? And since side channels was important for itself, we had a separate, lecture for it. But generally, physical side channels considered hardware security. Hardware security itself is like a very, very large area. There are multiple different things that you need to know about it, and there are lots of different areas people are working about on it. In this lecture, I'm gonna divide it into 2 main parts. The first one is what's called like hardware security primitives. Mainly, we're gonna talk about PUFs. I'm gonna describe what they are, TRNGs, true random number generators, and we're gonna also talk about tamper-proof hardware. Okay, so these are mainly hardware primitives. These are actual hardware modules that we build into our hardware in order to provide some security services. So for example, PUF, physically unclonable functions, is for creating keys and managing keys. True random number generator, as the name suggests, is basically what is used to create random number generators. So this would be the first part of the lecture. Hopefully we can go over it. And then the second one is what's called supply chain security, okay? Supply chain security in this specific case is the way that we build the hardware, for starting from the design all the way to the point that you actually start using it, okay? And as far as we were concerned with the talk in this class, we always said that, oh, okay, the hardware that you get at the end of the day is secure, right? But all of these is based off this assumption that the supply chain for creating and building the hardware is actually secure. And unfortunately, as we're going to discuss, this is not true in most cases. In many cases, especially the trend that I'm going to describe and show it to you, it shows that you have to even be more worried about this. So we can no longer assume that all the hardware that you're getting is completely what we are expecting. Okay, and specifically, we're going to see 2 main things. The main one is what's called hardware trojans, which basically is modifications in hardware that can create some malicious activities. And the second one is generally how we can protect our IP, which is our hardware in this case. Okay. So that would be the second part of the today lecture. So let's just start with the first part, and hopefully we can cover both. If we didn't, then probably some part of the Tuesday would be on part 2. Okay. So if you recall, early on in the course we talked about trusted platform modules, right? And we said that basically this is where we put our trust and we start the trust. And we said that generally this trusted platform module is this unit in hardware that has all the cryptographic pairs that we need to, some cryptographic functions and all those things, right? But of course the question is, how do you store these keys? Because two types of attacks can happen, right? One is that when your hardware is off, right? So for example, let's say this is your TPM, this is your general hardware. When your computer, for example, is off, maybe the hacker can actually probe this TPM, open the box of your computer, open the enclosure of the computer, start probing things and see if they can read it. And another thing that can happen is that during the interaction between when your computer is on and your TPM is being used, maybe during that interaction between TPM and the rest of the hardware, the attacker can actually read this information. We usually call it physical tampering, which means that the attacker tries to physically read off these values. The easiest thing to do is basically we have an oscilloscope, for example, or we have a digital to or analog to digital converter, a DAC, and we've just literally probed that pin in the hardware. Okay, so you can actually read this values up. Okay, so in that case, the question is, how do we secure that? Because obviously, you cannot just, if this is your TPM and this is your CPU, for example, and there are actual wires between them. If you want to, for example, encrypt something, you need to actually send and receive the key, for example, right? And if somebody basically listens to these pins using measurement equipments, they can actually read what you're sending and receiving, right? And that will break the assumption that we had that these are perfectly secret, they're in isolation and so on and so on. Okay. So in order to fix this problem, so as I said, this is basically the possible attacks that can happen: probing while the data is being read from TPM and reading the information while the computer is off. So to solve this problem, one solution that's very widely used is what's called this tamper-resistant hardware. Okay, so tamper-resistant hardware is this physical type of solutions that we add when we're manufacturing the hardware in order to make it tamper-resistant. So for example, there is a specific type. For example, there are specific type of enclosure that doesn't allow the pins to be exposed to the outside, so you cannot really measure it from the outside. So if you're familiar with PCB design, we can actually have wires at multiple layers. You can also have some multi layers and have the wires in the middle. So kind of like your wires is actually, unless you completely breaks off the PCB, you cannot really read off those pins. Okay. So there are, physical actual solutions to make sure that pins, for example, cannot be read. If somebody wants to read it, they have to just, destruct the hardware, and you can actually figure out that somebody is trying to tamper with your hardware. Another thing that's being done is we talked about electromagnetic side channels, right? So we said that basically what would happen is that your transistors is switching, right? And that creates some electromagnetic emanations that comes out of the device. What we can do is that when you're building this transistor, when you're manufacturing these transistors, usually there could be layer of metals that you can add on top of it, and this way you can significantly reduce the amount of emanations. So these are basically at the device level you can make these changes. It's It's too physical, so I don't want to go into the details, but have this in mind that at the physical level, when you're actually manufacturing the hardware, both at the transistor level and at the circuit level, when you're like, putting these different devices together, there are all multiple ways, there are very advanced ways of making sure that this information doesn't go out. Okay. And typically, this is all referred to what's called tamper-resistant hardware. Okay. The downside with it is, of course, that increase the cost because you have to add this additional layer of security added to your manufacturing. But for specific and important use cases, including, for example, military applications, sensitive applications, and so on and so forth, tamper-resistant is actually is very widely used and very popular. Okay, so many of the advanced devices that's being used in sensitive application mainly are all tamper-resistant hardware. Okay, so it's not like a regular memory or regular CPU is actually tamper-resistant. And this basically not only helps you with the probing, but also helps you with all sort of different digital side channels. Physical side channels. Temperature could be shielded, emanations could be shielded, and so on. Okay, so that's one way of fixing this. If you want to learn more or interested in hardware manufacturing, you probably can go and dig a little bit deeper on how tamper-resistant hardware is actually being manufactured. Okay. So just quickly before jumping into the second solution, if you remember, we talked about hardware side channels and how we can fix physical side channels. If you remember, we said that basically adding randomness and changing the hardware was one of the solutions. This is kind of like the same realm of tamper-resistant hardware, basically. There's this notion of what's called hardware masking, which generally these ideas, including adding some additional hardware piece into your system or adding this enclosure to your system, all considered hardware masking, and basically they're generally categorized as tamper-resistant hardware. Okay, so just a quick recall to what we discussed last week, for physical side channels, you can actually use this hardware techniques in order to mitigate. Okay. So now going back to our problem, the problem is that we want to store keys and we want to interact the TPM with the rest of the hardware. How do we actually build hardware in order to be secure? And we said that one solution would be tamper-resistant hardware. Like we physically build hardware to be resistant against this. It comes with some cost. It's not something that you regularly can use in normal, consumer grade systems and laptops and computers, but in sensitive applications, that's what we want to do. Okay. Another solution is what's called, kind of dynamic solutions. So the idea is that instead of actually storing the keys, literally storing the keys, how about you create a mechanism, creating a function that generate those keys on the fly? The good thing about this is that you never then need to store them, so you never be worried about, oh, what would happen if somebody tries to probe it, because there's nothing there. You never store the actual keys in your computer, so whenever you need them, you create this this magical module that creates the key for you. So you just query it, and then it gives you the key. Okay. So that could be some sort of, another possible solution. And good thing about this is that you don't need tamper-resistant hardware anymore. You can just use this in order to create those keys for you. So how do we create that? The idea is what's called a PUF, a physically unclonable function. Okay. So basically, what PUF is PUF is a piece of hardware that you send a request, which we usually call a challenge, and based off that challenge, it gives you a response, and this response is basically going to be for a given challenge. We know what the response is, and this would be our key for this challenge. Okay, so basically, this would be the key that we're going to use. We send a specific challenge to the PUF. The challenge for now, assume that it's just a regular input. And we get an output of that function, and that would be our key. The important thing about this is that this is hardware is unique for each hardware. So it's not like you can build the same PUF and use it on different computers and send the same challenge. For the same challenge, you will receive a different response for every single different hardware. And that's why you have a specific key for this hardware. We're going to describe how we can do it, but generally the idea is that this piece of hardware magically gets this inputs and creates some sort of a random output. And that random output that's what you can use for keys.
If we send the same challenge over and over again, will it always give us back the same key?
Yeah, if on the same hardware, you should get the same key.
Is it dangerous?
It might be or may not be. We're actually going to discuss a little bit about that as well. Okay, so we get the general idea of what is a PUF. The PUF is this piece of hardware. It's literally a piece of actual hardware that wait for some challenge. It could be multiple different challenges. It doesn't have to be just one challenge, and creates a response for that challenge, and that will be the key we're going to use. So now the question is, okay, how do we build this PUF? What exactly do we need? I mean, a little bit more detail, right? So the first thing we need to understand is what is the threat model? Like, what are we trying to protect from? And the threat model for PUF is basically we want to have these two things. The first thing we want to have is that we want to have something that is very easy to measure, but on the other hand, hard to predict. Why should be easy to measure and why should be hard to predict? The reason is that you want, as a user, you want to be able to quickly send a challenge and receive a response, right? So measuring it, in other words, sending the challenge and getting the response should be easy, should be quick, because you want this key to, for example, encrypt something. If it takes hundreds of cycles to generate that key, then that defeats the purpose. But on the other hand, it has to be hard to predict, okay? So if the adversary doesn't have access to the PUF, it shouldn't know that, okay, if I send this challenge, that would be the response. If the adversary can predict this challenge response relationship, basically it means that the adversary has access to the key, okay? So the only way that we get the response that we want is actually having the hardware itself. Think about it as an oracle or as a function, right? So if I have the function, I should be easily get the response that I want. If I don't have the function, then I shouldn't be able to. If I don't have the function, then I shouldn't be for a given challenge. I shouldn't be able to see what the response is. Okay. If I could, then I basically break the security assumption about this device, okay? And another important thing is that assuming that I have access to one PUF on device number 1, I should not be able to detect what would be for the same challenge, what would be the response for device number 2, okay? So I bought 2 same laptops, 2 MacBooks. I have one and I have access to PUF, the first one. I can send as many as challenges as I want and get as many as responses as I want. But knowing that information should not be good enough for me to detect and predict what would be the response for a given challenge on laptop number 2. Okay, so that's what we want to protect. And another thing is that from one input to another input, the output should look random. Because again, if the output is kind of like dependent on the input, then the adversary can figure out a mapping between the input and output and tries to predict what the output should. Okay. Any question at this point? So the idea of a PUF is actually quite nice. In order to get this and to be unique or hardware specific, people have found a few decades ago that what we can do is actually using the physical characteristics of the hardware itself to create this randomness for us. And they're actually banking on this idea that if we build multiple hardware, exactly the same hardware, let's say multiple CPUs, when we are actually manufacturing them, there is a slight difference between each of them. All right, 1, 2, 3, 4. These are, think about it as some sort of a noise. These are manufacturing noise. So when you're building hardware, depending on, for example, which part of the wafer you are building your hardware, depending on the temperature and the condition of the manufacturing equipment and so on, the characteristics of this devices are different from each other. The main thing is the delays of the gates in each of these devices will be very different from each other. So for example, if I build a full adder multiple times, the time it takes, for example, the full adder number 1 to add 2 numbers together would be T1. The time it takes for the full adder number 2 to add those 2 numbers would be T2. And it's very, very likely that T1 and T2 are not equal to each other. Why? Because generally the way that we build hardware, we build silicon, it's slightly, there is slight, intrinsic randomness that involves with it. Okay, it's just because of the physical characteristics of your transistors. Okay, and as a result, if we build different hardwares, the delay characteristics mainly would be very different from each other. And what you can do is that now you can actually profile this delay characteristics and know which hardware has what delay characteristics, and this way you can maybe build a PUF off of that. Okay, so the general idea, to repeat, is that given that when we are building hardware, we have this intrinsic, change and differences, randomness in them, you can actually be smart about that and use that in order to build something to be a physical unclonable function. Okay. So the interesting thing about this is that it has 3 specific, properties. First, it's going to be very, very, very difficult to replicate. Okay, so if I build 2 hardware, and this one has delay characteristics, T1, and this one has T2, I cannot easily build another hardware T3 and say, oh, I want to build something that looks very similar to T1, because as I said, these are natural changes. It's not controllable changes. So you cannot really build something that is the exact replica of one of your devices in terms of delay characteristics. Okay, so it's very, very difficult to build that. And that's very good, because if I have a PUF in device number 1, I cannot go and build a new device that has the same characteristics with device number 1. I cannot, mimic device number 1. I cannot replicate device number 1. And that's where the security of the PUF in device number 1 is coming from. Okay. The second nice thing about this is that measuring it is very trivial, because basically what we're going to show later on in this lecture is that basically measuring this is as simple as measuring how long it takes from here to here. Okay. For example, for the full adder, we're not going to use full adder. We're going to use a different circuit. But generally, in order to measure the delay, all you can do is just measuring from the beginning to the end. How much does it take to do that? Okay, and there are ways to measure that in hardware. And so that's, remember I said that measuring it should be trivial, but predicting it would be difficult. That's exactly what we have here. Measuring it's very simple. Predicting it and replicating it is very difficult. Okay, and finally, the only way that you can predict this is just using brute force. So basically, in order to know for a given challenge, how long does it take for example, this full adder to generate the results for you, you have to basically literally send this challenge and wait for the response. And assuming that this is basically, let's say, 2 to the power of 32, like 32 bits adder, in order to measure all the challenge, you need 2 to the power of 32 different pairs, right? And this number is huge. So it's not something that realistically you can do. And then if this number is big enough, like 1 to the 128 or 256, then you have to measure to the power 128. These are the numbers that takes years and years to basically prove. Okay, so that's very similar to encryption. That's where the security basically comes. Okay, any questions?
Here we're brute forcing. What are we trying to find?
Here,
Yeah.
so for example, you want to find, if I send challenge, let's say 0101, and how long does it take? For example, if I want to add 0101 with 000, how long does it take to until I get the final answer?
Okay, and where does the 2 to the power 32 come in?
So for example, this is the number 1 challenge, right?
Yeah.
So this will be T1, for example. Now I have another challenges like 10101 plus.
To figure out all the challenges.
Yeah, it would be T2, T3, T4, right? And these numbers are slightly different from each other. Okay, because they're involving different gates in your system. And in order to, for example, find this, this is 2 to the power of 4. This is 2 to the power of 4 as well, right? This is the number of attempts you need to do in order to have a full coverage of all the challenges, right? And now think about this, instead of 4 bits added to 4 bits, now you have 64 bits added to 64 bits, right? So that's where it becomes very challenging for you. Is that clear? Any questions? Okay. So 3 interesting things by using physical characteristics, mainly delays of network, is that the first thing is replicating them is not easy. The second thing is that measuring them is very trivial. And the third one is you cannot predict it unless you actually do the proofs. Okay. So now that we have this tool, what we're going to do is that in order to use this for the purpose that we wanted, basically creating random keys, what we can do is that we're going to build the PUF unit, the PUF unit for hardware number 1. And as the manufacturer, when we're manufacturing it, we can have basically a profiling phase where we're going to send a bunch of these challenges. And we're going to measure, the response. And what we're going to do is that we're going to store this securely somewhere, these, let's say, 4 pairs. And this would be our secure keys, okay? During the using of this, what we can do when this hardware is actually in use is that we're going to send this challenge. We already know what should be the response, right? But the adversary has no idea what this is, right? So the only thing that we need to keep secure is this table of challenge and responses, which actually the manufacturer only has it, nobody else has it, okay? And if a user wants to, for example, know what the keys are, they have to directly contact with the manufacturer and get this table, okay? So a secure user can always contact the manufacturer and get this table, but a random adversary can never get that information, okay? So it's kind of like, a secure way, similar to the way that we start communication between 2 parties. Remember, we said that, they should first agree on the key and then they can use that key. This is the similar way. So we basically, burn that key in the hardware. Nobody can read it except the manufacturer. The manufacturer has that idea, that information. And if somebody, for some reason, wants to use those keys and wants to know what those keys are, they have to directly talk to the manufacturer and say, okay, I bought this device, I don't know, serial key XXYZ something. And remember, each of these instances of even the same device has a very different characteristics, okay? So each one has a unique table. Oops. Each one has a unique table like this. So you basically send the serial number, you get the table that you want. But it's not like, every random person who wants to read the table, the table will talk to, for example, Intel and say, oh, I have this device, give me the table, right? So there should be some secure way of communication.
So this is like at the time of manufacturing, or is it like a real-time thing where you send like an IP request to something?
So at the time of manufacturing, the manufacturer builds this table. Then if the user wants to use it, then they have to decide when is a good time for talking to the manufacturer. It could be during real time, but in most cases, what you would prefer to do is there's an authentication phase in some sense where you basically get this information beforehand.
What does the user need this table?
The user may not need to use the stable. They may, because so assuming that so that's a good question. So some cases you want to have access to the key. Some cases you don't. I'm just saying that if you for some reason you want the keys, you want to know the keys as the user, as the owner of this device, that's the way of getting it. But in some cases you don't need to, because generally you don't care what's your secret key in your computer is, right? So you can just, all you care is that your communications is secure, right? But for example, think about this scenario in which that you want to do something like a MAC or digital signature or something from your hardware to someone else's hardware. Then in that case, you need a key to for example, sign it or something like that. Right? Is that clear? Any questions? Awesome. So let's actually see some examples. So far I gave you kind of like, some arbitrary example of a full adder and say basically, you have inputs and then you have outputs. And one big question is that how do I measure this time in hardware? Because we want to measure this delay in hardware as well. So let's see how we actually build PUFs in reality. The idea of PUF is basically what's generally we call is silicon PUF, because this is actually, actually implemented in hardware. So generally, when we are saying PUF, it means silicon PUF. So what we are doing is we are building two. So the general idea is this: that we are building two combinational logic paths. This combinational logic could be a full adder, could be just a simple multiplexer, could be any combinational logic that you probably know already what they are. We build the exact same logic. So the combinational logic on the top and bottom are exactly the same full adder, exactly the same multiplexer, whatever. But since we are building these two in the same hardware, on the same hardware, they're not going to have the exact same delay. So the delay for this one, let's say T1, for this one is T2. I already described why these two won't have the same delay. So T1 won't be equal to T2, all right? So what will happen is that at this point, if I send the same input, so if I send input X, of course, both of them gonna give me Y, right? Because they are exact same logic. But the time for this one, the time it takes from this input propagates through here to here would be T2. For this one, it would be T1, and these two times are not the same. So what we're going to do is basically I'm going to use it like this, like a latch or a flip-flop, where essentially the time it takes for this value to get in and this value to get in are different, and based on that, the value that I'm getting at this point is going to be different. So, for example, what I'm doing here is that let's say that for now, before actually sending this is equal to 0. Okay, so I'm just sending zeros, and this 0 is going to propagate one way or another. Let's say for now the challenge is also all zeros. So what will happen is that all these muxes going to get these values, right? So it's, the control bits of all these muxes are 0, which means that just all of them will pass 0. So basically, this one would be this path all the way, right? And then you're going to get 0 here. And then for this one, you get this path all the way to get 0. Okay. So now think about the time that we are basically sending a pulse, sending a 1 to this input. So the 1 starts, this one gets, with some delay gets 1, this one gets 1. Then again, still assume that the challenge is all equal to 0. So with some delay, which is the delay of this multiplexer, this point also becomes 1, right? Again, with some more delay, this part also gets 1. And then the story continues, and then at some point, this one becomes 1 as well, right? And the delay it takes from here to here, it basically depends on this multiplexer, all the way to all these multiplexers. Let's say they have n of these multiplexers, okay? So it takes n of the combination of n of these multiplexers to this point becomes, jumping from 0 to 1. And interestingly, the second half, the bottom half, has the same story. So at this point, this is 1. With some delay, this becomes 1, and so on and so forth, until this point, this becomes 1. And if you look at this point, basically what is happening is this bottom line is connected to the clock, right? And this top one is connected to the data, okay? So what will happen is if I look at the signals of these two, if this one is the clock, this one is the data. So if the clock is 1, and if data is already 1, so at this point, basically, this Q gonna get sampled, right? So this Q gonna get sampled, and then this point is 0, and it's gonna get 1. Okay, so this would be our Q. So if this line is faster than this line, Q would be equal to 1. But on the other hand, assuming that this scenario where this line is slower than this line, so basically clock becomes 1 at this point. So at this point, the positive edge of the clock, the value that's Q gonna sample is the value of this D, which is equal to 0. So at this point, Q stays 0. Okay. So basically, all we are doing with this, this innovative kind of design is that if the top half is faster than the bottom half, Q will be equal to 1. If the bottom half faster than the top half, then Q would be equal to 2. Okay? So basically, this Y is completely dependent, this value of Y is completely dependent on these delays of the boxes. And as I said, when we are building these boxes, this would be very, very random. So we don't have any control of how much delay this mark is going to have, how much delay this mark is going to have, and so on and so forth. So if you build this 100 times, there will be 100 different variations of this, and all of which going to be, some of them randomly going to get 0, some of them going to randomly get 1. And for example, if I build 100 of these, very likely 50 of them would have Q equal to 0, and 50 of them have Q equal to 1. Okay? Probably, almost, if we build this right. And what I can do is that if I want to have, for example, a 128-bit key generation mechanism, all I need to do is that replicate this 128 times and have 128 of these Qs. And I already described that how each one would be very random. So I have 128 random bits, and each one would be different from the other. So we basically have a list of 128 bits, all of which are randomly generated. And the nice thing is that they're different from one hardware to another hardware. So there's no way of predicting which one is which bit is which. And that's exactly what you want to get from a PUI.
So they're deterministically random for the hardware? It's like the sliver path is what's kind of.
Yeah, so the reason that you're getting that randomness is, for example, in this specific case, is because these muxes, so the propagation delay from here to here for this mux number X is different than this mux number Y.
Okay.
Right? Just because you're building two different gates and they're different. And so this point to this point is different from this point to this point. And once you cascade them all together, the whole delay path would be different from each other.
Wouldn't there be different latencies from like a select bit on the 0 side versus the select bit on the 1 side.
Yeah, so that's where the challenge actually comes into play. For now, just assume that challenges are all zeros, but now that's where you can now play with these numbers as well. So remember, we said that what we want to create is we send a specific challenge and we get a specific response, right? And we want to say that, okay, challenge 1 has response number 1, challenge 2 has response number 2, which are different from response number 1. How do we play with that? That's, if you look at here, it's basically the challenge in this specific case is the controller of this multiplexer. So for example, if I change from 1 to 0, now the path changes from here to here. Right? So 2 separate paths, 2 separate multiplexer. And I already told you that these multiplexers are all randomly generated. So the delays are actually very different from each other. So basically, using this challenge, you can create all different combination of multiple different muxes in this design. And this way you can basically have all the randomness that you want. Does that make sense? So in other words, what we are really doing here is that we are banking on this fact that these muxes are not similar to each other. And using this flip-flop or this latch, we are basically translating this process variation into an actual number. And using this trick of controlling with multiplexer, you're actually controlling this path for each of this top path and this bottom path using this challenge. So if I change the challenge, if I change 1 bit of challenge, either the top half would change or the bottom half would change. And this way I can create multiple different challenges and multiple different responses. Does that make sense? Okay, so there are, there are proof of why, PUFs are secure. Generally, what you want to have is these 3 things: the uniqueness, the uniformity, and reliability. These 3 things. So uniqueness means that if I build 2 different PUFs, PUF1 and PUF2, if I send the same challenge to them, same challenge, I should get 2 unique responses. That these 2 response 1 and response 2, should not be equal to each other. So they should be unique from each other. Okay. So in order to show that your PUF is secure, you have to show that statistically these 2 responses are unique. Uniformity basically says that if you do this, like for example, 128 bits of these, it should be uniformly distributed between 0s and 1s. So ideally, what you want to have is that for each single bit, the chances that this bit is equal to 0 or 1 should be almost equal. Should be 50%. Okay. Otherwise, if one of your bits is more biased toward 0 or more biased toward 1, then what you would get is that the adversary can basically predict that this bit is most likely 1 or most likely 0. So basically, you're reducing your effective size of your key at least 1 bit more. Okay. So you want uniformity basically, which means that you want to make sure that bits across the 128 or 64 or whatever number of bits you have, they are uniformly distributed in your PUF. And not only for this PUF, but also for this PUF and for any other PUF that you get. And finally, reliability means that if I repeat the same challenge over and over for one PUF, I should get the same response. Okay. So it shouldn't be, oh, this time I send this and I get a different response. So you should always get the same response for all of them. So this is reliability. So basically, these 3 things that you want to have when you're building your PUF systems. And generally, there are 2 main applications for PUF. Remember, we wanted to create keys, okay? So you can either use this directly for encryption. So basically, in this case, that would be a key generation or key derivation application. Or you can use it for also what's called authentication. So authentication for this case that, for example, so as a server, I want to talk to multiple different devices, device A, device B, and device C, okay? So how do I make sure that I'm indeed talking to device A and not an impersonator of A, which is like, for example, A prime? How do I distinguish between A and A prime? What you can do is that basically using this PUF system. So you basically, instead of sending the communication, sending the message first, you send the challenge to A and you wait for the response that's coming from A, okay? And what you know is that as a server, you have access to that challenge response table, okay? So you know that, for example, if I send this challenge to A has to give me this specific response that I know I get it from the hardware manufacturer. If that happens, and if I get that response from A, I can trust A. And how do I trust? Why do I trust A? Because A prime is a different physical device, and I already told you that building a PUF, a replica of a PUF, is not a simple task. So there is no way that another device can replicate the exact same PUF. So what will happen is that once I get that response, it is guaranteed that it's going to be A and not going to be A prime. Okay? And then same story for B and same story for C. So this is like usually what's would be a use case for your PUF in authentication. So it's not going to be used for key generation, but in this case, it's going to be used for authentication. Okay. Any questions here? Let's have a quick break and then we're going to come back in 3 minutes and continue. All right, let's continue. So two different applications, right? We either need it for key generation or we either need it for authentication, okay? Based on these two applications, we have generally two classes of PUFs. We call them weak PUF and strong PUFs, okay? So weak PUF is generally, so it's not, doesn't mean that they are weak in security-wise. Weak means that there is only a small pair of challenge and responses that this PUF can generate. So for example, if I go back here, the number of challenges that and responses that this specific PUF can generate is 2 to the power of n, which is the number of bits for this challenge, okay? So, and then if this n is large enough, that's a huge number. But there are other types of PUF that they only get one or very few number of challenges. So you cannot use this kind of design. They are called weak PUF, and they're usually useful for using keys and using it for encryption. Why? Because for encryption, you basically just need one or multiple pair of keys. You don't need 1,000 keys or 1 million keys, right? You just, for each specific device, you probably need 1 or 2 keys or multiple keys, right? And the good thing about weak PUF is that building them is more reliable. So for example, one specific type of PUF that's being used a lot is what's called as SRAM PUF, okay? So the way it works is this, that people have found that, if you have an SRAM with multiple rows, when you power up your SRAM, the value each line, each cell of this SRAM gets is completely random. So it could be 0 or 1. And anytime that you do this, it's basically going to generate the same key for you. And in this case, your challenge is only 1 bit. It's basically off or on, right? So once you turn it on, it's going to randomly initialize to specific initial state. And people have found that if you build this SRAMs right, from one SRAM to another SRAM, these bits will be different. And what they use this for is that, okay, this could be our secret key for each different device, right? So all we need to do is basically just know what is this initial state is, just record this, and then basically that would be our key. So anytime we want to create a new, anytime we want to use the key, we just turn on the computer and we have the key, okay? So this is usually called a weak PUF, okay? And the nice thing about this is, it's once your computer is off, there's nothing for the attacker to see, right? So as I said, one example of a weak PUF is a power on state on an SRAM. There's bunch of others as well, but this one is like the one that's very widely used. The second group of PUF is when we are using PUF for authentication. And for this, we need a large set of challenge response pairs, a large set of CRPs. And we usually call this strong puffs because we have a large set of challenge responses. Why do we need a large set of challenge responses? Remember, going back to the scenario said that, okay, it's a server, this is device A, this is device B, this is device C, right? So what you want to do is, if I send this challenge number 1, I want to get response number 1, right? And I said already that replicating A and creating A prime is difficult. So it's guaranteed that whenever I send challenge 1, I'm going to get response 1, and A prime cannot mimic that, okay? So I get the security that I want. But now think about that the next time I want to communicate with A, what should I do? So the next time, if I send challenge 1 again, I'm going to get response 1 again too, right? But this is not secure. Why? Because I already used this challenge response pair, and A prime can actually listen to this communication because this communication is not secure. And then the next time, although the first time A prime cannot impersonate themselves as A, the second time they can because they already know what the response should be, right? So they can basically just record this communication, and the next time is just repeat that value that it's supposed to say, okay? So we usually call this a replay attack. You basically, because of replaying the same information, the attacker, although it cannot on the fly generate this, can record and memorize this answer and then give it back to you, okay? So what should we do to prevent this is that the next time I'm going to send a challenge, I don't send challenge 1 again. I'm going to send challenge number 2, and I'm going to get response number 2. And as long as this challenge and response is only used once, you're completely secure because regardless of how many times the attacker sees this, we're never going to reuse it, okay? It's very similar to the nonce idea, okay? So we are basically only use nonce once, and in here we also use the challenge only once. And now you get the idea why we need a large set of CRPs, because if I want to communicate multiple times, 100 times, 1,000 times with A, anytime that I want to communicate with A, I need to send a new challenge. And few bits doesn't work for us, right? So we need a large set of challenge responses so that I freely can send as much as challenge as I want. And if this number is big enough, let's say, again, going back to 128, this means that millions and millions and millions of challenges, okay? So for the entire lifetime of this device, I'm completely secure. Does that make sense? And how do we build this challenge responses is basically, one of the ideas is already showing it here. So basically, this is the example of a strong silicon, okay? Because basically, as long as your challenge is, this n could be 128 bits, it could be anything, right? So this way I can get what I want. Question? Okay. So one important thing about strong PUFs compared to weak PUF is that since we are kind of using it for authentication, the adversary sees both the challenge and the response, okay? And if we keep doing this, the attacker has access to a very large list of challenge and responses, okay? Although this is not a security per se, a security issue per se, because as I said, as long as you use each challenge only once, you're completely secure. What the attacker can do is that use this to build a model, which is usually a machine learning model, to predict what is the behavior, what is the relationship between the challenge and responses. Remember, I told you that an important part of a secure PUF is that the attacker should not be able to predict this, right? And that's what we want to have. So for strong PUFs, you want to be able to be resistant against this type of modeling attacks. These days, machine learning is like the main way of doing this modeling because machine learnings have been very, very successful of modeling things that we necessarily don't know what the relationship is. So what we need to do is making sure that our design is secure against these. What should we do? We basically, there are lots of different research proposals on how do we, change things in our design to make sure that the machine learning cannot easily catch it. If you're interested, I suggest and I recommend you to go and read a little bit about machine learning resistance PUF design. But generally, the idea is that you want to make sure that the adversary cannot easily model your challenge response pattern. Okay. So that's kind of like it for PUFs. One final thing to mention is the challenges that we have with PUF, and it's kind of like where we are with PUF in the state of the art. One of the key problems with PUF is dealing with the noise. So remember, we said that basically the way that PUF works is that we have two different paths, right? A combinational logic at the top and a combinational logic at the bottom. And then we're gonna basically using a flip-flop in some sense to get the response, right? And we said that basically intrinsically the delay for this and delay for this are different, and that's how PUF works. Unfortunately, another thing is that can change the delays of these two are variations because of the environment and temperature. So if this device gets hotter or gets colder, these delays also change. So the values that when we measure this when we were manufacturing it was at a certain condition, right? At certain degree, at certain environment condition and so on. But when we are actually using this device, the temperature might change, might go up, might go down, might go at different location with a very, very different environmental characteristics. And what would happen is that we are expecting to see that, oh, challenge 1 has response 1. But since the temperature has changed, this delay has changed, and then as a result, instead of getting challenge response 1, I'm going to get response X. And these two may not be equal to each other. So this is what's called a reliability issue. Is that for the same challenge that we are expecting to see the same response, the results that we are getting are not exactly the same. How do we fix that? There are multiple ways that we can fix this issue. One is creating some sort of changes in the hardware itself that instead of measuring the absolute delay, we usually measure the difference between these 2 points. And if we do that, then if the temperature goes up, the temperature goes up for both of them, right? So both for the top and bottom. And in that case, nothing really changed. The difference doesn't change. So if you do kind of a differential measurements, you can fix that issue. I'm not going to show you the details, but just have this idea that you can design it to be more robust against it. Another way of fixing this is error correction codes, ECCs. You probably have heard about ECCs before in SRAM and your memory. These ECCs is like the way that you encoded your data, and you kind of can detect bit flips in your data using those flag bits that you have. So you can use ECCs for your PUF as well, and it's actually very extensively being used in the literature. Okay, so that's number one. You need to deal with the noise. So error correction, differential dependencies is what we usually do to fix it. There are also, all other challenges and research questions. For example, the overhead, the strong pulse and being resistance against machine learning, using different technologies and what I just described. For example, people have shown that instead of using SRAM, maybe you can use another technology to create weak pulse and so on. So there are lots of different ideas that be floating around. It's a pretty established area, so it's not like there are things that are very dynamically changing. It's not as similar, for example, to digital side channels where things are moving and changing so fast. But still, there are lots of ideas of okay, what can we do in order to make these pods more secure. Okay. Any final question about PUFs? So let's move on to the second security primitive. Remember, we're still on the first part that we are talking about secure primitives. If you go back earlier in the class, remember we said that we need randomness. We need randomness for our encryption algorithm for the initial vectors. I remember when we talked about pseudo-random functions, we said that we need some seeds. We need some nonce and all those things. So there are, and then this is just not for encryption. There are lots of other scenarios that you need randomness in your computers, in your program, right? Where that randomness is coming from, how do we create that randomness? That's the responsibility of what's called a true random number generator, or a TRNG. A TRNG is again literally a piece of hardware that you design and you put in your system, and whenever you need to have something random, you just collect it and query that module. The fact that it's true random number generator is that, of course, you can have a pseudo random number generator, right? TRNGs, and you probably know how to create that. So, for example, you can have what's up? Oh, so you can have, for example, a bunch of flip-flops, and this can create some notion of random number generators. But these are pseudo-random number generators. They're not cryptographically secure random number generators. What you want to use in your secure applications is what's called a true random number generators, okay? And for true random number generator, what you need to have is something that is uniform and sufficient entropy, which means that it's random enough. And if you recall when we were talking about what is random and what is not random, I told you that there are standard statistical tests that you need to do and pass in order to show that something is random and not random. This is basically the same issue here. So if I'm building a hardware and I'm claiming that this is a true random number generator, I need to pass those tests. Okay. But another thing that we should pay attention to is that since this is actually a piece of hardware and we want to use it in real time for encryption, for decryption, for nonces, for all those things, it has to be fast. It has to be low power and it has to be low cost. Okay, so you cannot create a true random generator in hardware that takes multiple cycles to give you that random value. Why? Because you want to encrypt something very fast, you want to decrypt something very fast, and if you need a random number for that encryption or decryption, you have to query this random number generator, and you have to get the response that you want pretty fast. So on top of actual challenges in building this from the security perspective, there's also practical perspectives that you need to pay attention to. Low cost, low power, and being highly performant. Very important. Okay. So how do we do that? The idea is kind of very similar to PUFs. We also use physical phenomena that we have around us in order to create that randomness. Thermal noise, for example, people have shown that the thermal noise, the changes in the temperature of the device, if we can actually use that, we can use it for creating a randomness. And this is, people have shown and proved that this is actually a very good source of randomness, and we can create a really nice random generator with this. Photoelectric effect is another thing that people can use for creating randomness. Okay. I'm not going to go through the actual implementation of it. Again, if you're interested, go and check it out. Like, for example, how two random number generators are implemented in hardware. But just have these, 3 bullet points in mind that, not everything that, just, sampling some random behavior automatically becomes a true random number generator. In software, you cannot usually create a true random number generator. What you need to have is a true source of entropy, true source of randomness, and you need to sample that in order to create your true random number generator. And for all the security purposes that they discuss in this course, the cryptographic algorithm, AES, RSA, etc., you need an actual true random number generator. Okay? You cannot use a pseudo random number generator and think that, oh, this is good enough. Okay? So just be very careful when you're designing your crypto algorithms. It has to be a true random number generator. There is also a lot of works on how can we create TRNGs using these new technologies. So for example, another big use case of quantum computers is actually TRNGs. These days, and cell phones and etc., people are pitching the idea of having something quantum related in order to have that true random number generator. And the assumption that this could be one of the first real use cases of something that's quantum related. Okay, so there are new paradigms that people are thinking about to create this randomness. And again, the idea, if you remember, is that it has to be secure, but it also has to be fast, and it has to be, low power or low order. Okay. So we want to have both of them ideal. And that's why we need to come up with new physical characteristics and new physical design. Okay. Any questions about TRNGs and PUFs? And generally, security primitives? We good? Awesome. So this is kind of like the end of the first part about the hardware primitives. We mainly covered the main 3 things: the tamper-proof hardware, the PUFs, and the true random number generators. There's lots and lots to talk about these. They actually can have their own lecture. But I just wanted to give you some high-level idea of how to build these, okay, and what is important. For true random number generators, you probably, if you're into it, I definitely recommend you to spend some time and read more about them. How do we create? Okay. So now let's move on to the second part of the lecture, the hardware security, and that's what's called a hardware supply chain security. And this is actually very, very interesting problem. It's becoming more and more important these days. And if you're into the news and you're following the news, there are lots of efforts, the billions and billions of dollars actually that the United States particularly is spending on this in the previous 2 years. So let's actually see what is the problem and why should we care about this. Okay. So basically, to give you a quick definition of what we're talking about, we're talking about the attacks and defenses during the design and manufacturing of the hardware. So any sort of hardware that you use, whether it's an FPGA, it's an accelerator, is it your CPU, is your cell phone, whatever it is, during the process of building this hardware, if there is any sort of issues, and we're going to talk about what are those issues, this is basically related to what's called a supply chain security, supply chain hardware security. Okay. So this is kind of like, a quick photo of things that we need to be worried about. I'm going to go through them one by one with a little bit of more detail. But generally, this is the IC lifecycle. So this is how you create an integrated circuit. So you start with some IP vendor. The vendor is the designer, right? So they basically design this and think about it at system level. Then they write some HDL code probably, right? Some hard level description code like a Verilog or something. Then we go to the system on a chip design house, or basically this could be the IP vendor itself, or it could be a collection of IPs that goes together to build the system. So for example, your cell phone has chips from multiple different entities. So one is coming from Apple, and there could be some coming from Qualcomm, there could be some from some other companies, and so on and so forth. All of them connected together to create what's called a system on a chip or an SoC. You put them all together, and then that's where you have the design of all of these things. Still, the design is in hardware description language, so there's nothing has been built yet. Then you send it to some foundries. The foundries is where this is being built. Foundries these days are extremely expensive, and it's very, very high tech. So it's actually, there's only a handful of these foundries around the world. Mainly the ones that are being used these days, it's what's called TSMC, which is this company in Taiwan, which basically I would say, like, I think the majority of all the chips that are being used in your cell phones, in your laptops, especially new technology like 5 nanometer and 7 nanometer, they're actually being manufactured in this company. So even, highly sensitive applications and devices should go there and be manufactured there and then come back. And you can kind of see what the problem is, okay? And then once you have this, then we go to the development phase and deployment phase. Essentially we get our chip back and then we start using it, okay? So what are the challenges? Basically, this is what's called the attack vectors, right? We're going to talk about this, but as you can see, the keyword in most of them is what's called a Trojan. And then the second issue is going to be something what's called a cloning, okay? And these are the two things that we're going to talk about. What is a hardware Trojan and what is cloning? The general idea is that during this process, either the designer or the manufacturer, the foundry, can change this hardware in some malicious way, okay? And this final user has no idea that what will happen, because all the user finally gets is this piece of chip that has no idea what is inside it, how to test it, and so on and so forth, right? And the interesting thing is that both the IP vendor and the foundry can be the culprit. It's not just the designer. The foundry can also make some changes to your hardware, and that could create lots of problems to our system. So actually, let's go and see what are those problems. So again, to give you some background, you probably heard about chip manufacturing and shortage. You probably heard about this $37 billion bill called Chips for America. So as I said, this is actually strongly motivated by the U.S. government to fix this issue, and very interesting to know about actually. So let's actually see what is the problem that can be created. What the attacker can do. If you go back during this class, what we said that our fundamental assumption always was that we can trust hardware, right? And when we are saying trust, it basically means two things, right? The first thing means that when we are saying trust, it means that we are assuming that the hardware does what it's supposed to or advertised to do. So when we are saying, oh, SGX should create isolation, we are assuming that hardware does that isolation for us. So if the SGX, if the Intel does not do that isolation for us, then all these other algorithms that we talk about, like attestation, key exchange, and all those things, would not work at all. And there's no way that we can do anything about it, okay? Because we are fundamentally assuming that the hardware follows what we are assuming it follows. If it doesn't, then there's no way that we can see through this computers, okay? And the second thing that we usually assume is that the designer also does not actively or intentionally change things, okay? And this can be true when we know the designer and we trust the designer. But as I said, for example, since we are sending these chips offshore, to another foundry in a different country, there is no way that we can make sure that that device and that manufacturing can be trusted. Okay. So, and unfortunately, it's not something that say, okay, how about we actually build it here? Since it's very, very high tech and very, very costly, it's not something that we can quickly do in the same country. And it's not just a US problem, right? Think about any other country have the exact same issue, right? So either you have to come up with foundries locally, or you have to find some way to trust this global this outshore foundry in order to make sure that they don't intentionally change things. Okay, and that's that's generally what we call a supply chain security problem. So what will happen is, in reality, what we are getting is what is very different than what we're expecting, right? So we are expecting to hardware does not always do what it's supposed to, and the manufacturer doesn't change things. But in reality, because we are giving this opportunity for the attacker to change things, at some point they evolve, right? So, and that's why we are seeing these issues. Okay. So the first thing that the adversary can do is what's called a hardware Trojan. Okay. So a hardware Trojan definition is intentional malicious modification in hardware. Okay. So the adversary intentionally changed things in hardware in order to do something. So hardware Trojan is kind of like synonymous to malware in software, right? In malware, what we do is we are creating this piece of software to do some harm, right? And then we manage to somehow, inject this malicious software into the computer and start executing it. Hardware Trojan is kind of like the hardware counterpart of the malware. It's changes that we do in the hardware. And of course, we need to find a way to actually implement that, right? So it's slightly more complicated because it's not something that we can do after the fact. Once the hardware is manufactured, then you cannot change it, right? But in software, you can actually change it after the fact. That's why you have like all these memory issues, you have these buffer overflow and all those things. For hardware, it's not the case. But for hardware, since we are actually cannot fully control the supply chain, it's difficult to make sure that the hardware is secure. For software, you can secure the supply chain, right? You can say that, okay, I'm going to design this software in this company. Everybody's going to stay here. You're going to know exactly who's working on this software, and we're going to have a control access to everybody. But for hardware, at some point, I need to ship this off to another country, and they're going to build this for me. And that's going to be the problem that we're going to face with hardware Trojans. Okay, so now we know what is hardware Trojans. So let's actually give a little bit details of how to build hardware Trojans, what are the impacts of hardware Trojans, and so on. Okay. So two ways that you can create a hardware Trojan. Either the designer can create a hardware Trojan. So for example, in the SoC application, let's say you are building a cell phone, an iPhone, for example, which has multiple different chips, okay? It has a Wi-Fi chip, it has an audio chip, it has a power management chip, it has a CPU and so on, right? And usually what happens these days is that each of these chips are being manufactured and designed by a separate manufacturer. It's not like Apple gonna design all of these in-house, okay? They're gonna purchase it from different companies. So what will happen is that the designer maliciously change one of these. So for example, the audio manufacturer for this chip gonna add something to the design for some malicious reason. And once we are combining them all together in the cell phone, then this basically maybe has access to the CPU, maybe has access to the power management, maybe has access to the Wi-Fi, and so on and so forth. Okay, so that could be one way of creating the Trojans. The second way of creating Trojan is during the manufacture. So these designs have no issues, so they're all perfectly designed, they all trust each other, there's no malicious. problem with them. But once we send this code to, for example, TSMC or any other manufacturing company, instead of building exactly this, TSMC gonna maybe add this tiny little things somewhere in this design. And given that they're literally the ones that are building it, they can just add anything else that they want to it. Okay. And then send this back to us. And as we're gonna discuss, it's gonna be very, very difficult to find this tiny little change in this piece of silicon. And this way we can have this additional hardware activity in our system, which we call it the hardware Trojan. Okay. And we're going to talk about how we can actually do this. Is that clear? Any questions so far? Cool. So this is kind of like a cartoon. It's kind of like show the same issue. So usually the design starts with some sort of a specification. Then we do the RTL design. And when we are actually doing the logic synthesis, basically the third-party designer can change these things. Can change the RTL code, can change the gate level design and synthesis and so on. Okay. Then we're going to have our physical design, physical layout. That's what we're going to send to, for example, TSMC. During the fabrication, TSMC or any other company, I'm giving an example, TSMC as like a very well-known company, but there's no known, attacks done by TSMC, just FYI. The manufacturing company can also, change these things during the fabrication. And then we're gonna get the assembly, get the IC, and then at this point we have the chip, but we have no idea that whether at this point or any of these points there was a malicious change into the system. So that's the life cycle of an attacker. Okay, and as I said, once the design is done, there's no way that an attacker can attack this hardware anymore. So if at this point we pass the test, then we can fully, trust this hardware. But the problem is that at this point there could be multiple different attacks already happening. Okay. So let me give you a very, very simple example of how a hardware Trojan works. So let's say that you have this simple gate, this NOR gate, and this is what you were expecting to, for example, manufacture. Okay, so you want to have A and B, and you are gonna get your C. And then this is one gate that you're gonna have, and you're gonna assume that, okay, this is the gate that I want to use. Okay. What will happen is that instead of actually either the designer or the manufacturer, one of these two, instead of creating this for us, it's gonna add two more pieces of logic to the system. Usually what's called a trigger and what's called a payload. Okay. So the trigger is, as the name suggests, is that under very rare circumstances, it's going to get triggered. In other case, we usually call the hardware Trojan dormant. The Trojan is not activated yet. Okay. So in normal scenarios, if the trigger is not activated, the C and C modified or C prime are exactly the same values. Okay. So there is no way we can figure out that there is something different in our hardware. But once the trigger becomes activated, then basically we can change this C to some C prime, and this time the C and C prime is not equal. Okay. Actually, if you follow the logic, you will see that, for example, if both A and B are equal to 1, basically what we're going to get is that the inverted of C is going to be to C modified. If there's any other value than 1, 1, then this is going to be 0, and then basically whatever we're going to see in C, you're going to get it on C prime or C modified. Okay. And why would this matter? So think about this as controlling some multiplexer in our design, controlling some bits in our encryption and anything like that, right? So basically what we're saying is that if both of these are equal to 1, we are just inverting whatever that value is. And we are controlling the logic in a way that we want as an attacker compared to what is supposed to be. That's just a very simple NOR gate. So I'm adding this two additional gates to the original gate, and this way I can control what the hardware is doing. Okay. And now think about this, that we can do it in a larger scale. So for example, I have a full adder that's supposed to sum these two numbers together. I'm going to add this Trojan here, which is basically just some number of gates that I'm going to add. And what I would do is that instead of like adding these two numbers, maybe subtracting these two numbers or whatever, right? So you can think about many different scenarios in which the attacker, under some specific circumstances, which is activated by this trigger, going to change this. Why do we need trigger? The reason that we need a trigger is that you want to be as stealthy as possible. So in other words, in most scenarios, you want your trigger to be inactive, so that if somebody tries to, for example, test whether this gate is generating the same results or not, they cannot detect that there is a modification in this logic. Okay. So for example, in this simple case, 0, 0, 0, 1, 1, 0 all create correct results. Only 1, 1 creates incorrect results, right? So basically, there's only 25% chance for detecting this error. And now, if you actually do this in a larger format, you can reduce this detection rate significantly, and that's what the attacker wants. He wants to be stealthy as possible, right? And that's why we need a trigger. Otherwise, what we can do is that we just simply change this to another gate and build that, and that would be by default. Our Trojans always will be active. But as I said, what we usually want to do as an attacker is to be as stealthy as possible, and then only change things when we need. Okay. So just very simple example, but you can hopefully you can clearly see that how this can be extended to a more complex logics. Okay. So now that we know that how a hardware Trojan might look like, basically these are actual hardware modifications that usually comes in terms of gates. So you change the gate, you add a gate, you change the wiring, etc., and you're going to create your hardware Trojan. So where you're going to add these, you basically can add this to any other module in your system. You can add it to your CPU, you can add it to your RF module, you can add it maybe to your crypto module, and so on and so forth. One of the papers that we're going to read this week is going to be about how we can create a Trojan on an RF Wi-Fi module. So basically, they show that what they can do is that they can communicate and create a communication to the outside world by just changing these tiny little things in their hardware. Okay, and that's why we go to create this hardware Trojans. And what to add is, as I said, as small as possible, because you don't want to change the hardware to be very easy for the defender to find this and detect this. Okay, so you have to be as small as change as possible. But on the other hand, you want to do something malicious, right? So you cannot just add one NOT gate to your design and think that, oh, okay, this would be enough because you're just gonna negate whatever it has. It has to be something that you have in mind. So for example, it has to be sending data out. It has to be a denial of service. It has to be something that is useful, right? So it's not trivial to just change things and thinking that, oh, okay, it's going to be useful. And it has to be very targeted, specific part of the circuit, but also very small. So the challenge of designing a hardware Trojan is also pretty significant. It's not something trivially an attacker can. And as I said, usually what we do is adding a trigger so that by default, the Trojan is not active. It's only active when specific criteria is met. And once it's that met, and then the trigger becomes activated and your Trojan becomes active. Okay? So one final thing before we moving on to another story. So how serious is this? It's very, very serious. The reason that is becoming more and more serious is that, for example, if you look at the trend of how many chips globally is being manufactured, for example, in the US, in 2021, I think it was only 80% of the global chip manufacturing was done by US. So we are potentially vulnerable to 82% of the chips that we are using in our everyday life, okay? And that could be a very big challenge. Specifically, for example, let's say that for some reason, country number A goes into war with country number B, and this country is basically the ones that manufacture these chips, right? They can easily say that, okay, you can kiss goodbye to your chips, and or you're gonna get something malicious into your system, right? So that's the problem that we're facing, kind of like a geopolitical problem. And then another thing is not only just the foundries is the problem, the third-party IPs is another problem. As I said, these days we tend to actually have multiple of many different chips on the same piece of silicon. If you look at your cell phones, your Galaxy, Samsungs, or your Google Pixels, or your iPhones, you will see that actually the chips coming from multiple different companies, and they all designed together in order to create your system. So it's not like oh, you trust Apple and that's it. It's actually Apple needs to find a way to trusting all these other sub manufacturers as well. So the trend is similar to many other trends that we discussed in this class, is that this problem is getting worse and worse, unfortunately. Okay? So I'm going to pause here, and then I'm going to continue discussing this, especially about how to defend this against this and so on in the next lecture.
Hi.